Hello, I'm Arun Kumar, an Android software engineer working on the app core team at Grab. Today, I'm here to talk about Grazel, a Gradle plugin we have developed at Grab to assist with our consumer Android applications migration to Bazel build system. Grab initially started as a ride-hailing app, but since then it has grown to support different services like food and payments in different markets, primarily in Southeast Asia, and we serve millions of users every day. Our consumer Android application is a super app providing entry points to different services owned by different tech families. It is a highly modular application currently on Gradle build system and has hundreds of modules and has contributions from hundreds of engineers every day. We liked Bazel's strong caching and parallel execution capabilities and believe that we could benefit from better build times by migrating to Bazel as our codebase grew at a healthy pace. But having such a large codebase poses a number of challenges. As it stands today, we might not have one-on-one feature parity between Gradle and Bazel. On the Gradle side, we have Android Gradle plugin to compile Android projects, and similarly, we have native build rules in Bazel. So when we use an exclusive build system feature, we might need to spend additional time refactoring the codebase to make it compatible with both the build systems. For example, build config fields in Android Gradle plugin provide a neat way to inject values into the runtime, and this is not something present out of the box in Bazel. However, it can be easily achieved with a custom macro that we can build. So when we talk about such refactoring tasks, naturally this takes effort from feature development, and there was a pushback from engineers because this effort could be instead spent on feature development. Apart from such refactors, writing equivalent Bazel build scripts is a manual task, and as per our internal estimations, we required considerable effort to migrate the project. Considering all these challenges, we had a couple of goals for the migration. While for a simple application, it might be possible to migrate the entire application in a couple of days, but given the large code base such as ours and the blockers we just discussed above, this is not something that is easily possible for us. So we wanted this migration to be incremental. By incremental, we mean that we are able to gradually migrate the project and look into resolving blockers discussed previously along the way. The main reason for this is that it can happen parallel to feature development, and this need not be a blocker and can be done like any other PR to the main branch that we have. This way, we can also ensure that we can establish strong feedback loops, such as having parallel CI builds on the main branch, on PR, and also we could look into building dashboards, etc. To help with these goals, we built Grazel. Grazel stands for Gradle to Bazel. Today I'm really excited to talk about the architecture, the functionality, the design decisions we took to build the plugin, and how it has helped Grab so far. Grazel is the core of our migration strategy and helps us in reducing the overall migration effort in a variety of ways. Firstly, it allows us to take a programmatic approach to migration where majority of manual and repetitive work can be automated. It allows us to keep Gradle scripts as a source of truth for build scripts, thereby reducing the maintenance effort when we have multiple build scripts. At its core, it is a Gradle plugin that works on any Android, Kotlin, or a Java codebase. When applied to a project, it registers few tasks that can generate valid build.bazel and workspace files. And finally, it adds incremental migration capabilities to the project which we will discuss later in the presentation. Now let's see how the plugin can be used. In the root build.gradle file, we can apply the plugin with the given coordinates and then configure Grazel with a couple of things like rules version, etc. Doing so will add couple of tasks to the project such as migrate to Bazel and format Bazel files. Now let's take a quick demo on Google's Topeka sample application, which is a Kotlin based multi-module project. Firstly, running migrate to Bazel task would generate all Bazel build scripts, and then we can even run the app using Bazel mobile install, which is a neat way to run incremental builds. Here, in the generated build script for quiz module, we can see that Grazel is able to infer various things like package names, Kotlin library, and dependencies. The same goes for other modules as well. While this works for simple applications, what about unsupported Android Gradle plugin features that might require refactoring? Our solutions to this problem is what we call hybrid builds. Hybrid builds works on the premise that a large project's module dependency graph can contain a variety of modules ranging from simple Java or Kotlin library to advanced Android libraries. Among these modules, some simple modules can be safely migrated to Bazel. Grazel can scan the dependency graph of a project and find such modules by performing a compatibility check, and then generates Bazel build scripts for them. Once build scripts are generated, these modules can be built with Bazel, while rest of the unmigrated modules can be built with Gradle. Now let's see how this can be achieved. Similar to Bazel's loading, analysis, and execution phases, Gradle has three distinct phases: initialization, configuration, and execution phases. Configuration phase is where the Gradle execution plan is constructed, and naturally Grazel hooks into the configuration phase. And since Gradle allows untracked arbitrary I/O during the configuration phase, Grazel does Bazel build on all the migrated targets, thereby generating corresponding build artifacts like AAR file or a jar file. Then it does something we call dependency substitution. For example, if a quiz module was migrated, it would either produce quiz.aar or a quiz.jar file when built. When a project dependency in Gradle is resolved, we check whether a build artifact already exists for that project. If not, we leave it as it is. However, if we do have a build artifact for the project, we remove the project dependency and then replace them with already compiled artifacts. Grazel does this on the entire project graph, and finally, when the execution phase begins, we use already compiled Bazel targets and then the non-migrated Gradle modules. The entire process can be controlled via a single flag called Bazel enabled. Having such a flag also means that we can run parallel builds on our CI and then have strong feedback loops on whether the whole Bazel migration scripts are correct. Having a hybrid build adds ability to incrementally migrate the project and then have feedback loops along the way. Hybrid build also helps in resolving blockers. For example, build config functionality that we discussed earlier can be implemented with a custom Bazel macro. And then Grazel can be modified to generate rules containing this macro. Now when we run the migration again, the new capability check would cover more modules and they also can be migrated. For example, Bazel build config macros. When we do this consistently, at one point it should be possible to have 100% migration. Hybrid builds also don't require any changes on the Gradle build scripts. Now that we have covered hybrid build, I want to talk in detail about Bazel build file generation. Generally, when we talk about build file translation, we can think of three distinct stages: a parser to read the source data and then convert it to an intermediate representation, And once we have the intermediate representation, we can adapt it to the format that we require. In this case, Bazel build files. However, Gradle plugins already have this parsed project information as Java objects. And through the plugins API, we can infer the project information as needed. This way, we are able to avoid a category of problems that would arise if we choose to write a custom Gradle scripts parser. For example, let's take a configuration for Gradle as shown above. We could get details such as plugins and extensions from the project object, and once we have this information, the remaining bit is generating the corresponding Bazel rules. So when we talk about code generation, we had a couple of goals for the design. Firstly, we wanted the ability to programmatically manipulate the rules from a programming language so that we can adapt the rules as we need. Also, we wanted the DSL to be flexible and extendable so that new rules can be easily added with minimal effort. Since we are working with Gradle plugins, we wanted it to be JVM based so that we can directly invoke it from Gradle plugins. We also wanted the code generator to be concise so that it is easy to work with and does not have any noise such would be present otherwise. For correctness and formatting, we could use existing tools such as Buildifier, and Grazel already uses Buildifier for ensuring the generated build scripts are correct and then also formats them. To achieve these goals, we chose to utilize Kotlin, a modern programming language from JetBrains, for creating a type-safe starlark DSL. It allows us to write valid starlark code naturally from Kotlin. As shown here, I'm using HTTP archive and Maven install functions naturally as part of JVM rules. We can see that it is very similar to the generated starlark code that would appear on the Bazel build files. At the core of the DSL, we have a statement interface that represents a valid starlark statement. From there, we have multiple implementations like assignment, array, functions, and objects. So the idea here is that we could utilize the provided abstractions and create new statements as needed. Now let's take a small example. An object statement is typically a collection of assignment statements separated by a comma and then guarded by a parenthesis. The core API is designed to be extendable for adding new rules on top of this. For example, let's consider writing a load function. We first start by writing an extension function on statements builder. The statements builder class is an abstraction that allows managing multiple statements and also can finally write the generated statements to build file. Extension functions are a Kotlin language feature that allows us to add functions and properties to existing types. So this way, using the statements builder, we can extend the DSL to cover more cases. So in the body, we simply add a function statement, and the function statement here would take care of writing a typical function syntax in starlark. Similarly, we can add another extension function for load. However, this time in the body, since we know the function name, we can simply delegate to the function method that we just wrote above. The idea here is that we can compose complex rules from the core DSL API. Here we see the implementation of Maven install rule that we saw earlier. As we can see, the load statement here can be naturally used due to the way the extension functions work. And the function abstraction here allows us to interact with it in a type-safe manner. So when we talk about code generation, we want to limit the number of edge cases that we might discover and have to deal with. One way to do that is to establish strong conventions that we can follow. For example, firstly, we want the Bazel target name to be always derivable from Gradle project name. This way, it would be easy to map dependencies and build files. Then we wanted to have a single build.bazel file adjacent to an existing build.gradle file. This allows us to easily map Bazel target name from Gradle project name. Finally, we wanted to have Gradle build scripts as source of truth until the migration is complete. To do this, we prefer to regenerate the build scripts when we want to make any changes. This way, it forces us to handle the edge case within Grazel and ensures that future invocations of Grazel does not require any changes and is compatible. Grazel forms the core of our migration strategy and helps in bringing the overall migration effort considerably down. In the future, we want to explore the possibility of generating granular build.bazel files as per Bazel's best practices for a Java project. Granular build.bazel file also helps in parallelization and caching and thereby helps in better build times. We're also excited to open source Grazel soon in Q4 2020. While currently we are focused on generating build rules, we also want to explore generating test rules as well. Thank you.